me tell you that we will, that some of us will be going to a talk by Norman Sleep on Stanford University in the geology department, and the place is the William Olson Saal. That is house, the Earth Science Building. I didn't bring a map, but if you were to walk, it would take you maximum half an hour. If you take the bike, it takes you 10 minutes.
Is it a university?
It's university, yes. Would anybody be interested in that? No.
A little too far.
Yes. Okay. Good. Therefore, then I apologize at least for myself being absent after that, which means we can give the word now to Tuting. She will be talking. So Tuting did her PhD thesis here at MISO in the metallurgy department some years ago, and has been is now working at the Danish Meteorological Institute, DMI. So today she will be talking, asking about a model resolution, whether it matters for climate prediction. Please. Hope have the exciting discussion after that. Please.
Yeah. I'd like to thank Excel first to give me the opportunity to come here and discuss and have the opportunity to talk with you guys, the experts, and I would very much like to show today that the problems we have experiencing in climate simulations and get discussions and hopefully also advices from you guys. As I said, in this study, we are mainly interested in how the model resolution will give us what's the meaning, what's the implication to our climate simulations. Now, before I go into the work we have done, I would like first to show present the idea of climate projection and prediction. It's very I guess it's very different from the numerical weather prediction point of view, because in NWP you interested in precise solutions, or at least give accurate predictions for the weather state of atmosphere for the particular time in the future. But in climate study, we know it's not possible because of the system is nonlinear. There are so many uncertainties in the system. Instead, we talk about I think until very recently we mostly talk about the climate projections. That means we try to know in advance what would the tendency will be in the future climate, instead of trying to answer the question of what's the exact temperature or precipitation by the end of, say, 2100 year at say December 1st. Instead of answer such kind of question, we ask what's the possibility of the temperature differences in relative to the present time. Here I show the global mean near surface air temperature anomalies in relative to the present day climate. That's represented by a 30 years mean. It's relative to the average of 30 years in around this period. So we see in this, these are a particular set of climate simulations using the global climate model, coupled atmosphere and ocean coupled. So we carry out those simulations using the historical forcing as much as we know now. In fact, those are the signified the coupled coupled model in the comparison project phase 5 that specifies the historical forcings in the past and also specify a number of future scenarios for the forcings, and then ask the climate modeling groups to do simulations using those forcings and to try to see what's the possibility for the future climate. And so the question is to answer what about the tendencies in the future, kind of statistics instead of a precise state of the atmosphere. So it's a problem to try to find out a solution of the model system in response to the external forcings of the whole climate system, such as the solar activities and volcanic eruption and also the pandemic changes. And now, starting in recent years, we also started to ask our questions of climate predictions. That means that we want to know, say, next season, next half year, or next year, what the climate would be. What would next winter as cold as this winter, or will it be much warmer? Such kind of questions. That is, we would like to know the kind of prediction that give us some ideas. Of course, we cannot answer in a precise accuracy in that sense, but still would like to know in statistical sense what's the climate would like for some time from now. Normally we talk about a time scale from seasons to decades, including years and decades. And so this is a question not only we need not only to know the tendency or the model response to external forcings, but we also need to know how the model behave in terms of the internal natural variability. So we are not we need not only to know the tendency of this smooth 10-year mean average, but we also need to know those small wiggles. Which state would be? By the way, this is could see before the 2005. It's so to say the historical simulation, and here we saw 3 realization of the model simulation, and this is corresponding to 2 forcing scenarios. One with so to say RCP 8.5. That's the assuming the global development in the future will be very rapidly, and so there are a lot of emissions and a lot of human activities will come into affect our climate system. And the other one is RCP 4.5. That is a moderate development with certain concerns of our environment.
Which model is this?
This is ECS. The new, so to say, the new model. We are new in the CMIP experiments.
But you got your CMIP 5 runs done already, have you?
Unfortunately, this has a bug in the model that the volcanic forcing is not taking into account, so we have to redo it. We had done a lot of simulations, but we had to redo it. What could affect our climate predictions? That's, as we said, that the external forcings, and then, of course, the initial states, in this case, we're taking into account, although the atmosphere state has not so long memories, but the ocean, in this case, is particularly important. So the initialization of the ocean state is a key problem for the Decatur or seasonal to Decatur forecast predictions in climate. And then another, as we all know, another source of the uncertainty comes from the model system. That could be our dynamics are not good enough. The physics is not representative enough of their probably unknown physics, and also the numerics. So here in the last case, it comes to the resolution problem that we would like to answer this. I mean, in the past, we had in all climate simulations, we have because of the time length we need to carry out in the climate simulation, we have to use a relatively coarse resolution in climate models. But is the resolution also important for climate simulations? That's a question we need to answer. So before we go into the climate, we know in NWP that the resolution is certainly important as increasing the model resolution. The NWP or the forecast the quality of the forecast improves a lot. Then to the climate problem. By the way, now because our experience of the importance of the resolution for the NWP, at European Center now they are running the forecast model at something like 16 kilometers resolution, and according to European Center, they have a plan that to increase the resolution to something like 10 kilometers by the middle of this decade. So as the NWP increasing the resolution more and more, the climate simulations are also using a higher and higher resolution. In the last IPCC report, most models use the resolution of T42 to T63. That's is about 150 to 200 kilometers resolution. If we look at the progress of the resolution in the past, so this is about the maximum resolution in the past IPCC reports. Those models used in IPCC report. In the first IPCC report that's published in 1990, the model resolution is about 500 kilometers. So it's really a cost, and Europe has only a few grid points. But now, in the last IPCC report published in 2007, the highest resolution in their climate simulation, in their couple of models simulations are T106. That's equivalent to a little bit more than 100 kilometers resolution. And so the question is that as our computer power become more and more powerful, do we need also increase the climate model resolution as following the pace as NWP? And now we know that most model participating next IPCC reports would be at the resolution somewhere around 100 kilometers, depending on the complexity of the model. So we would like to know, we would like to understand. Is there any limits? Do we need to keep increasing our model resolutions for climate simulations? And if we increase the resolution, what that implicated to the internal variability in the model? How do they behave? In particular, we know for the seasonal to decadal forecast, so to say, the climate regimes as Brookings, North Atlantic oscillation, and such climate patterns would be important effect. And with these phenomena gets better predicted as we increase the resolution. So that's the main motivation of my study. So I would like to show some results. First, to answer those questions, we used the atmospheric components of the Easy Earth model. This component basically is from the European Center's atmospheric model, IFS. So it's the atmospheric only model without the ocean. Instead, we put a constant forcing for the SSTs. Sorry, not constant forcing. The forcing using using the error 40 SSTs and CIs. And then we have 4 model configurations at a different resolution. The first one is, so to say, the very low resolution one. That's only 250 kilometers by 250 kilometers. And the second configuration is the moderate resolution. That is T159, equivalent to 125 kilometers resolution. And then we have 2 high resolution ones that's similar to the original Kami model resolution. And then for each resolution, we make an ensemble run of 3 members. And to start the model, we selected 3 different initial states, starting from the summer and autumn and the January. So we think 3 months apart of the initial state should give a relatively independent model state to start. And then we look at the characteristics of the circulation in both in terms of mean and the variation. And then we also look at both ensemble means and also a little bit of spread. We haven't done very much studies about this yet, but we look at a little bit of the spread. And we compare it with the error 40 to evaluate the importance of the solutions. And then in the analysis, we mainly focus on the northern hemisphere winter. So first I show here is the zonal mean temperature average from all the 30 years in the simulation for different resolutions as a function of the height and the latitude. So here is the northern hemisphere winter. As you see, the first impression is all resolution has similar error pattern, except that the very low resolution has much larger bias compared to the others. On the other hand, once we go to the 159, the bias is reduced a lot in the whole, most part of the troposphere. But as we go to higher resolution, we didn't get very much in terms of mean. It's similar pattern and also similar.
When you speak of bias with respect to what?
Respect to error 40 and error entry, the 30 years mean. So I take the model 30 years mean and compare it to the 30 years mean of the error data. And both the model is forced by the SSTs from the same period. So
and you've averaged over the 3 ensemble members for each resolution.
Yeah, in this case. Yeah. And if we look at this is the surface mean sea level pressure, again at 3 months average, and the colors now are the bias in relative to reanalysis data. And again, the very low cost, very low resolution model has those stronger colors, meaning that it has larger biases. And then the all the 3 are again have similar patterns and a similar magnitude of the bias pattern. So it seems maybe as the high resolution in high resolution the bias is reduced a little bit, but not as much as I would imagine. So those are the means.
Just to be a little bit provocative, Shruti, I mean, they look all about the same to me, and you could imagine, I think, that what we're seeing here is different projections of the same bias. So, you're very unlikely to get warming. What have you got here? Warm biases in both the northern and southern hemispheres. So You know, in the very low resolution, it's ended up in the northern hemisphere, and in the higher resolution, it's ended up in the southern hemisphere. But this could be the same. You know, this could be a manifestation of the same model problem, and not a resolution problem. Yeah, I mean, I don't think there's any. I don't think you could attribute any physical cause to the fact that these bias patterns are different.
Okay, you mean something more substantial, like one thing I could think about is the model is similar Lagrangian model in losing mass over time. That could be one thing that you see the large bias in the polar areas. So that's the thing. I guess it's more fundamental.
Yeah, I just think that yes. I mean, I don't think we can judge on the basis of the patterns alone that there's a resolution issue. I think we could just be seeing the same model error projected in a different way in the output.
I mean, if this would be a resolution issue, then you would expect that the bias actually goes down if you increase the resolution. But obviously, that's not the case. So you would. So it's really a bias which doesn't really depend on the resolution, at least for the higher.
Your point is extrapolated below the mountains. Maybe if you get higher mountains, you get larger errors in extrapolation.
Yeah, that's another thing. I mean, in the Antarctic, maybe we should not take the surface to. Maybe it's better I show another map.
The mountains become higher, and then you have a large extrapolation error in the diagnostics.
Maybe I could show the 500 geopotential height. This is more systematic without the impact by the surface. Again, you see a slightly larger bias in the lower, but this one is bad, and then you still see a larger bias there. But to the highest resolution doesn't seem to improve.
Does the bias actually get larger in the Pacific?
In some areas. But here, I mean, I don't know. I didn't make a global mean or the hemisphere mean. In this sector, it seems smaller. So maybe a global mean. I mean, if you calculate the index, then maybe it's not so bad. But at least it seems to me it's not significant. But if you said that this is something a projection of some fundamental of the model errors, then I have to think about what it could be, and hopefully that can help European Center. But anyway, so I also look at the variability. So to see the variability, I use the low mean square. The geopotential height of the monthly mean. So here shows the error, the reanalysis data of the 30 years. Of the 30 years winter months monthly IMS, and this represents the variation of time scale longer than a month, because I have done the monthly mean and also then including the interseasonal and interannual variability. So compare this with my model. Now I show again, this is the ensemble mean. Indeed, again, the very low resolution is very bad, in particular in the Atlantic area, missing completely the activity center in North Atlantic. But then as the resolution go a bit higher, it seems at least the patterns are there for the ensemble mean. And but for the Atlantic, it seems that it's overestimated the activities in the higher resolution. In our resolution, but the B511 is particularly high. And so from the ensemble mean, we could see the model underestimated the variability over the Atlantic. But then I examined each members. So here shows that for all the 4 resolutions of each member, and it's it seems to me it's rather case dependent. I mean, if you look at, for instance, this moderate resolution, in one member that we see the activity center is too far south compared to the reanalysis, and then in other cases it's better. Anyway, it's very individual dependent. So it seems to me it could be that 3 members are too few for getting to catch the variabilities in such a situation. But on the other hand, it's expensive to make climate simulations, so I keep asking how many are enough, how many do I need to do, what's the minimum?
What happened to the third high resolution ensemble member?
I actually have 3, but I didn't. The third one was from another computer, another institute, so I didn't really get the analysis done. But I mean, if you look at the 2 members, the centers are completely off, or not completely off, but it's way not coincide very much. So yeah, this comes to my question: what's the smart way of designing the ensemble members, and then how many do I need? And if I look at further, I mean, now I just look at the general aspect of the variability, and I would like to also answer the important question to the local or regional people. For instance, for Europeans, we would like to know the NAO. Do we have predictabilities for the North Atlantic oscillation? Can we do predictions on it? And now again, I have the reanalysis data. The pattern I use the orthogonal analysis, and this is the first EOF and the first EOF for all the model resolutions and reanalysis. And the patterns are quite similar, except maybe, I mean, I calculate the correlations. Correlation to the cost resolution is not very high, but for all other resolutions, they are rather high. And so it shows the patterns are quite okay to get the right spatial correlation or spatial pattern for European or Atlantic European sector for the winter. But that seems not too bad in our models. I think I could skip this the PNA, the Pacific North America pattern. Again, they are very similar, except that the cost resolution that has lower correlation. But then I look at the time series, the corresponding time series. And now the black, I'm sorry about the quality, but the black one is from the analysis. You could see from the North Atlantic oscillation, they don't seem correlated at all, although I forced the model using the same SSTs as the analysis.
Is the time series for the full year or only for the winter months?
I think I plotted in months and weeks.
But
so
for each month of the year?
For each winter month of the year. So 3 winter months of 30 years. And I have removed the seasonal cycle from the data. So yes, I collect the winter monthly means and put them together and do the UF analysis. And anyway, yeah, it just looked at the Pacific may be correlated better, but still you could see something. A lot of places are completely out of phase from the model. The models are more like each other than the analysis.
So in the late 90s, there was this positive trend in the NAO. Do the models reproduce this trend?
I think 30 years are too short for that.
This was only in the 90s, starting I think in the late 80s to early 2000s that you would see the series.
It doesn't look
with our
have
eyes.
any change at all. I mean these are the whole 30 years, and it doesn't seem to have changed in the.
Yeah.
Of course, there are some periods like this is I started 79, so this should be the 90s. There are more negative here than in this period, and now in the it's more negative again. Maybe that's some indication. I didn't do a very careful analysis to look at the trend.
Okay, so these are ensemble means for each resolution, or are they individual realizations?
This one actually is ensemble means.
Okay.
Yeah. If you look at the individuals, they are also different.
Do they become more similar as you increase this resolution? For example, between 319 and 511, now they become closer. I cannot see it here easily. No.
No. Well, I have in another analysis, I look at the correlation, but I only look at one resolution. That apparently as I look at the higher levels of the model, then the correlation actually is better. But I didn't compare the differences between different resolutions. So from this, it looks like there's no predictability at all. cannot do anything about it, or we have to find a smarter way. And if I go on now, I would like to give a little bit focus on Brocken events. But Brockings, we know the Brockings has a huge impact to our weather. Also the seasonal mean. For instance, past the winter, or in this case, I brought the winter February 2005. Anyway, in this month, this is the monthly mean. It has a huge, very stable Brocken events in the Atlantic sector. As you can see now, the colors are the anomalies of these months to the long time mean. And you can see clearly that there's a Brocken in the Atlantic sector, and this actually gave the very cold Europe, and also very cold North America. I think in the eastern part of the states it was very cold, but in some part of the Canada it was actually very warm. Brockings are normally last long. That although it's kind of it lasted longer than the normal synoptic events, and it has normally has a huge impact on the extremes, and in the summer it could be for instance the drought events in Europe, and in the winter the cold spot. And so I do some analysis on the. So I try to see if because in theory the Brockings could be it's a kind of a stationary state. So there's theories that the Brockings are developed and maintained because the small scale waves, the small scale waves keep pumping energy into the mean state. So it maintains this high Brock situation. And if that theory plays important, then we know the resolution is certainly important for Brocken, the maintenance and establishment. So here I compute the Brocken frequency. That is the Brock days, the percentage of Brock days in the whole, in this case, in the whole 5 months winter. And now the orange color are the low resolution, the light blue are the moderate resolution, And then dark blue, the high resolution, the red is very high resolution in comparison with the reanalysis data. And now it's very clear that the coarse resolution, now this is the European sector, Atlantic and European sector, we see two maximum favorite blocking positions for the circulation. One is over the Atlantic and the other over the Pacific. And for the coarse resolution, it certainly cannot catch these maximums in both areas. And the modular resolution also, you see that they're spread in one case that actually is not bad, but in other cases it's also missing quite a lot of block days. And in the Pacific sector, that's still the low resolution or the modular resolution is still bad. And then as we go to the high resolution, the 319 resolution that we see, actually both, I think there should be 3 somewhere. Anyway, it catches the peak of this maximum block area much better in the high resolution. And but still there are some differences in the Pacific sector, but people said the Pacific sector has different mechanism behind blocking events because the PREP2 plays another role in the whole small dynamic. So from this plot, it seems that the high resolution really gave some gain for the simulation. Now,
so this isn't a controversial result, is it? Because I think the weather forecasting curves also demonstrate very clearly that blocking frequencies match much better at high resolutions. So this is confirming stuff that sounds good.
Yes, yeah. In these cases, you really see the advantages that high resolution. But on the other hand, probably it doesn't need to have very high resolution as 511. I mean, if we think about the cost of the climate model, and improve. So we see in general we see improvement in the model climate, particularly from low resolution to moderate resolution. But on the other hand, maybe we don't need. And we also see that there's some improvements in the climate regime events that high resolution is more realistic. And but then we also see that there are large spreads in different members, and it looks like at least 3 members are not converging the results. And so we perhaps, I don't know, this is my question, how to do it? If there are any smarter way of doing the ensembles. And then so it seems that probably it doesn't need very high resolution considering the cost, because in my case, the 511 simulation, it's more than double of the other resolution, but the 319 resolution, and it's really costly. And in particular, it's not only the running time, but also the storage time. When the model resolution increased so much, and it's a huge storage of the data, it's just difficult to move the data around in statistics. Thank you.
Thank you. Thank you. Any questions, please?
Can you say again what was the oceanographic component of the model?
In this case, all those simulations are only with atmosphere, no ocean. Yeah, I have a fixed ocean with the reanalysis SSTs and CRs. So I hope that I could have a more clear answer to only the resolution involved.
Do you know if the high resolution versions have a somewhat realistic representation of the Madden and Julian oscillation in the tropics?
I didn't know. I don't know in my rounds, but the European Center always claimed that all the versions they have. I mean, 511 was once their operational resolution. They also claimed that they have pulled better simulations before they removed to the operational. But I didn't do any.
And there are lots of studies who shown or who provide evidence that the MJO might have a really strong impact on TNA or NAO. If the model are still not able to capture the MJO, that might explain some of the biases.
Yes, yeah. I need to do more the physical ground analysis. Yes.
Question. When you compare to the analysis that are made on low resolution, and can this have an impact on these results? And why not to compare directly to data instead of in the data space?
The data is much closer resolution. That in that case you overrode your advantage of having a high resolution. I mean, one thing is that your data has much closer resolution than another one. So the very small features might not be seen in your station-based.
Yes, the statistics, you compare a small number of points, but data have all scales, or most of the scales inside. I mean, it depends on
yes, but
what is
then,
data resolved
yeah.
in this case.
But then you cannot really see the patterns. I mean, you perhaps get something in time, but I'm more concerned about the monthly means. I mean, if I do predictions for climate, then perhaps the monthly means is more important. On that hand, I need a higher resolution. I mean, if you think about the predicting Europe, even you have even people use a regional climate model for downscaling, but if your global information mixing the blockings, it will never give you the information in the original ASEAN ones. So you don't have the extremes as you would expect.
So the atmospheric model will have parameterizations for sub-grid-scale effects in radiation, clouds, and convection. And those parameterizations will be resolution dependent because, of course, there's different things being screened out. So how much retuning was there of the code?
I didn't retune anything. It's everything. It's the European Center's.
Right. So you think, and what was the parameterization designed for? What resolution was it designed for?
This is the SAM model. The basis are the same as the reanalysis. So we are using cycle 31. So it's the same model as error 40.
Right. And of the resolutions that you ran, is one of them closer to the
high resolution? I mean, error 40 runs at the T159.
Yeah.
But the cycle 31 also used for operational. For a while, I think that time it was 500 something.
So your low resolution runs might just be detuned. Yeah.
I think the same could apply to the high resolution one.
But the high resolution ones have got the correct parameterization in the sense that they've been tuned.
Yeah, T62 was not tuned. That's for sure. And also, I mean, I was using T63 with 31 levels. That also used a lot of the interactions. So it may not be a fair comparison. I have the T63 there. But I think the other resolutions should be okay.
Any other questions?
Do you know of any theoretical, I mean, non-purely numerical evidence, I mean, which, according to which one could say that simulating the climate at a given scale should, in a sense, be sufficient, and any results other than just numerical simulation.
No, I don't know what I mean.
Well, there are obviously components in the climate and features which are very small scale, which have a strong impact on the climate. Let us take the case, let us consider the case of when you include the oceanic circulation. If the Strait of Gibraltar came to be closed, then of course, with no inflow from the Atlantic, but to totally change the climate of the Mediterranean area and beyond. But of course, that's not a question of regulation, it's just a matter of allowing inflow from the Atlantic into the Mediterranean, independently of which, of the width of the two. On the other hand, there are many, when it comes to parameterization of subglacial processes, there are many processes, anything with to do with the structure of the Earth's surface, vegetation, which obviously occur at scales which are much smaller than the ones which are resolved by the most high resolution. So, and we have simply no idea of how, real idea of how to properly represent the statistical effects of these small-scale variations in the surface of a continent. So,
boundary layers are very difficult.
the boundary layers are very difficult. So,
I think Tim Palmer has a number in his mind.
yes.
He wants 40 kilometres in the atmosphere. He reckons that's what it will take in a climate model.
Yes.
But he may have done a calculation to suggest that that's actually attainable in his lifetime. And then he set the target of some of this.
Okay, well,
It's doable.
taking it into account, available computing time.
Yes, he wants a pan-European consortium, which I presume will be based in Oxford already, to take the climate model to 40-kilometre resolution in the atmosphere.
And if you fix the horizontal resolution and increase the vertical, what would be the... You have some...
Yes, that's what I saw on Monday, last week.
sorry.
Yeah. But on that case, I mean, in this model configuration, there are pretty good presentation on the troposphere, the layers, and so I increased the model vertical resolution to include the stratosphere in the models, and it shows improved a lot, in particular in that part of the troposphere, and the improvement are not only in the stratosphere but also in the other part of the troposphere. And then in that simulation, I look at also the correlations between the analysis and the model, and it seems that the higher levels have a better correlation in the patterns.
Okay, if there's no further question, then let's thank Julian again. If people want to continue talking to her, that might be an opportunity, but the other opportunity is also for those people who want to go to Norman Sleep's talk at the geology department. It is possible to walk. There's enough time if everybody wants to walk. So there's Stockholm University